Welcome to the Microchip Stepper Motor Fundamentals Types of Stepper Motors Training Module. This module will discuss the main components of a stepper motor and how these components work together to actually turn the rotor. Also, 3 types of stepping motors as well as 2 subcategories will be explored. As the name implies, the stepper motor moves in distinct steps during its rotation. Each of these steps is defined by a step angle. Notice in the example shown here that there are 4 distinct steps for the rotor to make a complete 360-degree rotation, defining the step angle at 90 degrees. Since this motor does move in a discrete fashion, it can be said that a stepper motor is actually a digital motor. This characteristic makes it very suitable for digital interfaces such as with a microcontroller. Stepper motors are relatively inexpensive as compared to other motor types. There are a number of stepper motor designs that run from the most basic to very complex, depending on the motor chosen, the resolution required, and the application at hand will determine the cost of the motor required. More important is the fact that a stepper motor can actually be used without any type of feedback loop. Since the motor moves in distinct steps as defined by a step angle, only the number of steps needs to be counted to position the motor accordingly. This doesn't mean that a feedback loop would not be used in some applications. However, if feedback isn't required, board real estate can be maximized by minimizing these sensing components. The unique torque characteristics of the stepper motor make it ideal for position applications. In fact, stepper motors have been used for years in such applications as printers and machining equipment and will hold its position firmly at a given step, providing a relatively high holding torque. Other torque-related benefits include the higher torque and lower revolutions per minute than typical DC motors, as well as no need for mechanical braking. A stepper motor has some basic components. First is the soft iron stator. As the name implies, this is a stationary component. Each stator will be wrapped with multiple windings or phases that will be energized using a voltage source, initiating current flow through the winding to produce a polarity on each end, or pole of the stator. The rotor is the actual rotating component on the motor. This can either be magnetized as shown here, or non-magnetized depending on the type of motor. These different motor types will be discussed later in the presentation. In this example, if voltage is applied across the windings around a stator, current will flow through the winding. The direction of the magnet flux flow through the stator is determined by knowing the direction of current flow through the winding and then using the right-hand rule. Magnetic flux will flow from north pole to south pole, continuing through the magnetic rotor to the opposite stator pole. The flux will want to travel the path of least resistance or decrease the reluctance of the path. Since the rotor does rotate, it will position itself to minimize this reluctance. Adding more stators and phases in different positions, and then adding and removing the applied voltage on the windings will allow other stators to attract the rotor poles. The first type, already discussed somewhat in this module, the permanent magnet stepper motor, has a magnetized rotor. The next type, a variable reluctance type motor, replaces the magnetic rotor with a geared, non-magnetized, soft iron rotor. Finally, the hybrid type of motor combines characteristics from both the permanent magnet and variable reluctance motors. This type of motor offers very high rotational resolutions as well as improved torque. The permanent magnet type of stepper motor has the characteristic magnetized rotor. During the rest of this module, the nomenclature shown in this slide will be used. Each winding, although one entity, will be subdivided. For example, winding A is subdivided as A and A, and winding B as B and B. Keep this in mind while continuing through this presentation. The resolution of rotor rotation can be improved, decreasing the step angle, in a permanent magnet rotor by either increasing the number of pole pairs on the rotor itself, or by adding more stators and phases. Also, subsequent training modules will show that the resolution can be increased in a third way by using different stepping techniques. To rotate the rotor, voltage is applied to each phase sequentially. Again, current begins to flow, creating a polarity on each pole of that stator. Rotation in a particular direction is accomplished by applying voltage to the individual phases in a particular sequence. To rotate the rotor in the opposite direction, simply reverse this voltage sequence. Also, to hold the rotor at a particular position, step it to that angle and then stop the sequence while maintaining voltage on the appropriate phase. The next motor type is the variable reluctance type of stepping motor. This motor uses a non-magnetized, soft iron rotor that actually has teeth that are carefully offset from the stator poles to accomplish rotation. Notice also that the individual stator windings are configured differently than what has been discussed so far. All the windings have a common terminal that will be connected to a voltage source, while the opposite end of each winding is kept separate from the other windings. To increase the resolution on this type of motor, typically more teeth are added to the geared rotor. Each winding is again energized one at a time to create a polarity on the appropriate stator poles, and the rotor rotates to minimize the reluctance of the magnetic flux path. What happens next differentiates the variable reluctance motor from most other stepping motor types. Notice that to rotate the motor in a particular direction, the stator pole winding energizing sequence is actually reversed to that used in a permanent magnet motor. Also note that the motor's step angle is actually half that of a permanent magnet motor with the same number of stator windings. The last motor to be discussed is the hybrid motor. This type of stepping motor borrows characteristics from both permanent magnet and variable reluctance motors. This slide shows a side view of a hybrid stepper motor with the rotor removed. In addition to the rotor being magnetized, it and each stator has teeth. The rotor is actually in two sections or cups, one in the front and one in the back. The two rotor cups are opposite in polarity as shown in the close-up view of the individual rotor cup teeth on the right side of this slide. Notice that the teeth on one cup are offset by one tooth as compared to the other cup. This slide shows the hybrid stepper motor reassembled and turned for a front view. Referring to the winding diagram on the right and the stator pole configuration on the left, it can be seen that each winding actually energizes 4 stator poles at once when energized. Applying a voltage to each of the windings will control the direction of current flow, thereby controlling the polarity of each stator pole. For figure 1 of this slide, notice that stator poles A and A are aligned perfectly with one of the rotor cup's teeth, while B and B stator poles are actually halfway with half of the pole attracting one cup's tooth while repelling the other. The next step in the sequence, figure 2, changes the current direction in winding A while winding B maintains the same current direction. Now stator poles A and A are half on each rotor cup, while stator poles B and B line up perfectly. The rotor has rotated one step. The motor pictured has a step angle of 1.8 degrees, which is a significant improvement over the basic permanent magnet motor looked at previously. This chart compares various aspects of each motor type to make it easier to decide which motor suits the intended application. The first consideration is cost. The permanent magnet motor is cheaper due to the manufacturing process. Hybrid and variable reluctance motors have a more intricate fabrication process due to their geared rotors. The rotor is actually made up of thin laminates of soft iron, which reduces the occurrence of eddy currents within the rotor. A similar process is used when fabricating transformers for power supplies. Looking at the resolution of the step angle, hybrid and variable reluctance motors can achieve very fine resolutions due to the geared construction of the rotor, while permanent magnet rotors are physically limited by the number of pole pairs that they may have. Also, as with any stepper motor, as the revolution speed of the rotor is increased, there will be a pronounced decrease in the overall torque of the motor. Variable reluctance motor torque is maintained longer in relation to both permanent magnet and hybrid types. If noise is a consideration in the application, variable reluctance motors are typically noisier than their permanent magnet or hybrid counterparts. Finally, there are a number of stepping algorithms that can be implemented to produce a greater step resolution for a given motor. However, variable reluctance motors are limited to a single stepping algorithm. Therefore, the rated step angles for these motors are fixed. There are 2 subcategories of stepper motors which are determined by how the leads from each phase winding are brought out of the motor. The first example is a bipolar configuration where each winding lead is brought out separately. This type of winding, depending on the voltage applied and to which lead, can produce current flow in either direction, allowing each stator pole to be magnetized to north or south. The unipolar configuration, on the other hand, only allows current flow in half of the winding at one time. Notice that each winding has a center tap that is brought outside of the motor, along with each winding lead. In this example of a unipolar motor, the center tap lead is connected to a positive voltage source. As seen in Figure 1 of this slide, driving one of the leads on winding A to ground allows current to flow in one half of the winding, generating a polarity on the stator poles, and the rotor rotates accordingly. Next, Figure 2, the grounding source is removed from the winding A lead and one of winding B's leads is driven to ground. Again, current flows in half the winding and the appropriate stator poles are energized. Continuing the sequence will rotate the rotor 360 degrees. Again, bipolar motors allow current flow in either direction through each winding. Applying a voltage to lead A and grounding lead A generates current flow, resulting in the stator polarity shown here in Figure 1. Removing the voltage from winding A and applying a positive voltage to lead B and driving lead B on winding B to ground generates current flow and stator polarities as shown in Figure 2. Continuing the sequence will rotate the rotor 360 degrees. Comparing both winding configurations, unipolar motors can only allow current flow in half the winding, while bipolar offers bidirectional current flow. Since torque is related to winding current, bipolar motors will generate greater torque than unipolar motors. Furthermore, due to the fact that unipolar windings are thinner than bipolar motor windings, more wire is used, increasing the winding's resistance. This could cause increased power loss, potentially raising the temperature considerably. However, using a bipolar motor will require more complex circuitry, potentially increasing design cost, and use more board real estate. One final point, since unipolar motors do have both ends of the windings brought out of the motor, they could be connected in a bipolar configuration, omitting the center tapped lead. For more in-depth information on stepping motor fundamentals, please refer to the application notes listed above. Also, the Motor Control Design Center at www.microchip.com contains information for recommended products, application notes, and technical briefs related to motor control. The Stepper Motor Control PTM, found at the DigiKey website, continues the Introduction to Stepper Motors series and highlights various stepping techniques to improve motor resolution. In summary, stepper motors by nature are a digital version of a motor moving in distinct steps as defined by their step angle. There are three very different types of motors. One, the very basic permanent magnet stepping motor with its magnetized rotor. Two, the variable reluctance motor that characteristically offers a very high resolution thanks to the geared design of their non-magnetic rotors. And three, the hybrid motors, which offer the best of both worlds, using geared bipolar rotors to generate optimal torque and resolution. Permanent magnet and hybrid motors also offer a choice in winding configurations. Unipolar motors only support current flow in one half of the winding at a time, reducing the possible torque generated, while bipolar motors offer bidirectional current flow but require more board real estate to accommodate more complex circuitry.